All right, hello, welcome students. Let me work out another solution here. I got a question from chapter 31. It's number 29, and I guess I'll call this page 1, so we can have a couple pages here. I see there's a part A, B, and C. Let me just read it here. It says, a coil with a resistance R and N turns. And so down in the picture, they have this rectangular coil wrapping around, and so there's N turns of it and a resistance of R. Each of these turns has a length of L, and so the dimensions of this rectangular coil has length L and width W, so the area is length times the width. And then as shown in the figure, the coil moves into a uniform magnetic field at a constant velocity b. And then using the standard green here, let me make a little box. Let me not go all the way over. Here's my green box, and they show a magnetic field with little X's here, so that means the magnetic field in 3 dimensions is going into the piece of paper here. And so here's my B field. And let's see, what does it say here? So the coil moves into a uniform magnetic field B with a constant velocity V. What is the magnitude and the direction of the total magnetic force on the coil? And then there's 3 parts here. A, as it is entering the magnetic field. B, as it's moving within the magnetic field. And C, when it leaves the field. So I think the first part here is just conceptual. We got to put 2 things together. Is why would there even be a magnetic force? I mean, what is going on here? And this coil, this rectangular coil, as it's moving, certainly when it's outside of the magnetic field, there wouldn't be any change in flux. And therefore this chapter, which focuses on Faraday's law, which basically says a changing magnetic field makes an electrical field which makes the current, you wouldn't have any as long as you're outside. There is no change in flux. But I think you can begin to see that as this rectangle transitions from outside to inside, then there's going to be some changing flux. And because of that, there's going to be an EMF. And then, of course, an EMF with some wires and resistors then is going to make some current. And so the first thing is this, Faraday's law, but the second thing is Ohm's law, which says voltage divided by resistance gives you the current. And then the third piece, so I guess that's chapter 27, but the third piece is then in chapter 29, where we've learned that there would be a force on wires that have current in them, according to this equation. So as this thing enters the field, this rectangle enters the field, that's going to make a changing magnetic flux, which makes a voltage. Then Ohm's law says that makes a current. Then once you have a current, remember the current is in this magnetic field, or at least partially in, because part of it is in and part of it's going to be out, but then that's going to make a force. So that's the fundamental idea. It's these 3 pieces put together. I guess this is chapter 31, this is chapter 27, and this is chapter 29. And so let me take this as an opportunity to point out that chapter 31 is actually pretty short in terms of it's the shortest chapter, I think, in the entire book. It is really just Faraday's law, which this negative outside is Lenz's law, so that gives us the direction. But that doesn't mean the chapter is necessarily easy, because one of the things that you see right away is every time you start a problem in chapter 31 here about a changing magnetic flux then producing a voltage or an EMF, then that EMF results in secondary effects, which in this case is a current, and a current in a magnetic field creates a magnetic force. So we've got to put all the past things together, including things like direction, and we've got to then do the right-hand rule number 1 with a cross product, and we've got to do right-hand rule number 2 to figure out what direction the current is. And all of those are things of the past, but if we don't have a good handle on them, they kind of stop us from succeeding here in chapter 31. So 31 has its neat blessings, if you will, that it makes you review all these past chapters in order to move forward in chapter 31. So we've got a new piece that is kind of small in nature, but putting together with the other things makes this a hard chapter. So anyways, you guys have been working along with this. Let me just then answer this first part, which is A, which says, okay, so what happens as it is entering? So as it's entering, maybe I'll draw it kind of on a smaller scale, but right about here, I'll just kind of draw it maybe half in and half out, and in the process of moving the velocity v here, if I do this first calculation here, chapter 31, and say, okay, what is the EMF? Let me just do magnitude, so I'll ignore the negative sign here. My first reaction is to say, well, there's n turns in this coil. Okay. Then there's the derivative of the magnetic flux, and the magnetic flux is also an integral. It's an integral over the space or the area. Okay. Now, luckily for me and us here, taking this dot product, B, D, A, cosine, I can quickly say that it's cosine of 0 degrees because the magnetic field is going in, and the plane of the paper and the plane of this rectangle are the same. So that means the normal vector, and you could either say it's coming out or going in. So this is really either 0 degrees or perhaps 180 degrees if we wanted to make an issue about what is the direction of it. But we like to say don't worry about that, because that's either a 1 or a -1, and we're finding the magnitude. So call it 0 or call it 180. Either way, the absolute value is a 1, and we're trying to find that, so we'll just drop that out of the equation. Then I'll go on to say, look at the magnetic field. The magnetic field is a constant, and let me say it again, be careful with that word constant. Is a constant in space or a constant in time, or both? And in this case, they're trying to say the magnetic field is a constant in this space, so the magnetic field strength here and here and here are all the same, okay? But they're also saying it doesn't change with time, so I can actually then take this magnetic field and not only bring it in front of the integral, which is an integral over space, but bring it in front of the time derivative. So there's two calculus operations. And so constants can be pulled in front. However, you could have something that is a constant in space but not in time. So you pull it in front of this integral but not in front of the time derivative. And we see that a lot. Now, that's not the case for this problem. In this case, B is a constant of both space and time. So I will pull it in front of the time derivative as well as in front of the integral. Which makes this really nice, because what I'm left with now is just the integral of the area, which is one that you don't have to actually do anything. That is just the area. That's more of reading the math than doing the math. Okay, so there's the area. Now, the area is the area where there is actually a magnetic field. So keep that in mind, because when you add up the flux, you're talking about the area where there is a magnetic field, not necessarily the area of the rectangle. So don't misinterpret this, because if you misinterpret it, you might say, well, wouldn't that just be the area of the rectangle, and that doesn't change either? And so you pull that in front, you got a derivative of nothing, which gives you 0. And that's not what this equation is saying. This equation is saying the area of where there's flux. And so in this picture that I'm, half in and half out, if I kind of draw in blue, this would be the area. That's the area where there is a magnetic field. And that clearly is changing as it moves forward. And so there is a change with time. In fact, maybe we should do this. The area that has flux in it would have a width and maybe a length of x, not L. I don't want to call it L. That's the whole area of the rectangle. So this is a WX in my mind. And so as it's moving along, what changes is the x. The x does change with time. The x gets bigger and bigger, and eventually the whole thing gets inside, so it eventually becomes an L. So this is an N, a B, and then the width I can pull in front of the derivative, and then I have a dx dt, which then is the N, the B, and then the width. And then now dx dt is really just then the velocity. Which, by the way, as a side note, is the same thing we did with the motion EMF. We had BLV, where we had a metal bar, and we said the length of the metal bar would be the, we called it L, but in this case would correspond to the W, the width, and then the velocity. And then there would be N turns of them, or maybe you would say N metal bars. So this hopefully is not a surprise. In fact, we probably could even started this problem right there and realized that this is really just a motion EMF. And the fact that we loop it around just gives us the ability to have an extra factor of N, and it also gives us the ability to, oh, I lost my thought there. Well, the ability to maybe see a full rectangle in a flux. That's what I'm getting at. I know when we calculated the motion EMF, we made a mathematical rectangle. But this one, our mathematical rectangle, you know, is this, and it's getting bigger and bigger and bigger, and eventually get as big as the whole rectangle itself. Anyways, that would be step one, and that's really the part here from chapter 31. So that's the new piece of the puzzle. Let me continue to put this together with the other pieces we've learned in the past, and that would be starting with Ohm's law that says, okay, there's going to be a current, which is, I'll call it V over R, but in this case, the voltage comes from a motion EMF, so I'll write it as the script E, and we just calculated that that would be N, the B, the width, and the velocity, and divide it by the resistance. All right. So that's how much current we're going to have. So if we come back to our picture, as it's entering here, we might want to then say, okay, what direction is that current? Because would this current be set up in a counterclockwise direction, or would it be set up in a clockwise direction? And maybe I'll just make myself down here kind of a bigger rectangle. And maybe I'll draw a couple of flux lines going in. But I'm hoping you see as you move forward, there would be more. And so the amount of flux going in here is increasing. And we get the direction by what we call Lenz's law. It opposes the change. So if you imagine it moving forward and there's going to be more because of this field, the current is set up to make a secondary field that opposes this increase. And so that means it would want to make them come out. So I'm going to draw not only 3 new ones going in because of the external magnetic field, but the current that is set up then makes a field pointing out so that these balance each other and you're left with the same. And so that's what we mean by oppose the change. So this tells me that the current that is set up in this loop, whether it be counterclockwise or clockwise, is still to be determined, but I know it must be in such a direction that it would create a secondary field of flux coming out to counterbalance the new flux from the primary field going in. So here's where I'm going to do right-hand rule number 2. Remember right-hand number 2, if I use my thumb for the field, my fingers are the current. So now that I know the direction the field has to be from the current in the coil, this is the secondary one, I'm going to point my thumb out. I know that the field from the secondary, now not the primary. The primary is definitely in, okay? But the field that is now going to be formed, so I like to call it the second field, the secondary field. Whether it's clockwise or counterclockwise was to be determined, but the field would be pointing out. So I'm going to put my thumb and point it towards the camera here and say, okay, that's out. And then I'm going to look at my fingers, and my fingers go around in a counterclockwise direction. So if I would mark this, then the currents would be looking something like this. So it's a counterclockwise direction. And of course, the magnitude of the current, I didn't put a page 2 here, but the magnitude of the current is what we just calculated here. Now that we've done Faraday's law, and now we've done Ohm's law with it. Okay, that would be then the force. All right, so that's how much current we have. Now, the last part of this is now chapter 29, where we say, okay, now there's going to be a force. And this is what you get on a straight wire. So we might consider this loop as 4 straight wires. Maybe the top one I will call wire number 1, and then just going around in a clockwise direction, I'll call it number 2, number 3, and number 4. And so if there is a current in this top one going across that way, that's the direction of L, and then B is down into the paper. Now, again, I'm talking about B from the primary. I'm not talking about the field from itself. Remember, you can't put a force on yourself or a net force on yourself. So the field created by yourself doesn't make you go faster or slower. That's an internal force. So that was that whole discussion back in Physics 121 about internal and external forces. So I need to talk about the external force, which means it has to come from the external field, which I'm calling the primary field. And so here's where we're going to get into right-hand rule number 1. I'm going to do this cross product. So I'm going to put my fingers in the direction of the current. So that would be from, well, I guess this would be right to left. And then I'm going to rotate my wrist, not here, but here. So I close towards the magnetic field. So that's down. And you'll see my thumb pointing down. And so there would be a force downward from this top wire. Let me go to the right wire. Same idea. Current would be go up, close my fingers towards the magnetic field, and I would have a force on this wire towards my left. Okay. For wire number 3, I don't know if I can get my hand all the way around here, my right hand, and then I would put my fingers in the direction of the current and then close, and my thumb points up, and not a surprise, because it's kind of the opposite of number 1, so I expect to get kind of the opposite force. Now, maybe this is worth mentioning about number 1 and number 3 because it comes into play as I try to do number 4. Remember that this rectangular loop is only partly in. So when I say there's a force on wire number 1, it would only be on this little section that is actually in the magnetic field. The other part of number 1 doesn't have a force on it. Although that same story is true for number 3. So number 1 and number 3 are going to cancel each other off. Whether we're talking about just a little piece in, and so we're talking about a little bit of force, or we're talking about most of it in, then there's a lot of force, but there's a lot of force on number 1 and a lot of force on number 3. So no matter where this rectangle is, a little bit in or all the way in, the force on number 1 and the force on number 3 are equal and opposite. Although it changes because more and more gets in. But the point is I don't really need to calculate number 1 and number 3. They're going to cancel off. Good. But I said all that really more importantly for number 4 because number 4 is not even in the field at all while it's transitioning in. So for part A. Now part B, they're talking about when it's fully in the field. Okay, so let's talk about part B later. But at this point, as it's transitioning into the field, there is a current in number 4, but there is no field. And so this field would be 0 here. And so there'd be 0 force. So there is no force on section number 4 here. So there's only a force on wires 1, 2, and 3, and 1 and 3 cancel off. So really the net force boils down to just figuring out what is the force on number 2. We don't have to mess with the other ones. And I, of course, needed to justify that to you why we don't need to mess with them. So we only need to do this calculation one time for wire number 2. So let's do that. So I would then say the magnitude of the force, since I just did the direction, would be then the I, the L, the B, and the sine of the angle between them. So we just calculated the current a moment earlier. And so there's the current. I suppose I should be careful with L. L is the length of the wire. And as we study number 2 here, that's a W, not an L. So I'm glad they use a lowercase l here so that I wouldn't think that I'm supposed to use a lowercase l there. This would be another W, a width. And then there's the magnetic field. And then the magnetic field is 90 degrees to the current. So the field's going into the paper and the current's going up. So that's a 90 degrees in 3 dimensions here. Now, let me also point out that would only be the force on one wire. Remember, they said this loop is wrapped around n times. So every piece that goes up, every piece of wire number 2 that goes up would have that same force. So because of that, let me throw in the word total force and another factor of n. I say another one because the change in flux had to do with a factor of n. So if I put all these together, it looks like I would have an n squared. So I could also have a b squared. It looks like I'd have a width squared. I would have only one velocity and one resistance. And so that's the magnitude of the total force here. Now to make it a vector, I would put then a negative I hat direction. By the way, kind of a cheater's way, if you will, of mentioning the same thing here is whatever is happening here in terms of the current and the forces, it's got to be slowing it down, because when we are moving in and making electricity, making current, and the current runs through a resistor, that's making heat. That energy has to come from somewhere. And so it comes from the loss of kinetic energy of this thing moving. If we had done something wrong and said that the force was in the direction it's moving, that would be really, really weird, because what it would say here is that as this thing moves, it gets pulled in and it accelerates. So it's getting its energy from where? Plus it's making heat because of the current and gets it from where? And so there would just be a violation of conservation of energy. So it would just bother you immensely, hopefully, if you thought that it had to speed up. And so the fact that it slows down means it's giving up kinetic energy to make electrical energy, which then eventually makes heat. And so the conservation of energy falls into place here. All right, so this can lead on to B. B is much, much easier than A, because if we come to our first step here of Faraday's law, we can see that as the whole thing is inside, as it's moving along, there is no change in flux in this rectangle. It moves from one to another. Maybe another way of saying this, if you come back to the motion EMF, you could say this wire number 2 makes an EMF pushing current up. But now that wire number 4 is actually in the field, it would make an EMF pushing up. And it would be a lot like having a circuit that looked like this. You've got one battery representing wire number 4. You've got another battery of same magnitude representing wire number 2. And you're just not going to get any current from that. These two batteries are pushing equal and opposite, and the net current is 0. There is no net EMF. And that's exactly what the change in flux would be doing. So I guess I would write it this way. I have a minus an N, and I would have then the change in the flux, and the flux would be B dA cosine 0 degrees. But as long as the whole loop is inside, this would just be B times A, and the amount of change of flux would be 0. This is the total flux through it, and it's a constant value. And you take a derivative of a constant, and a constant in time, I should point out. It's also a constant in space, but what's important here is a constant in time, because I take the derivative of that, I get 0. So with a 0 EMF, and then I apply Ohm's law, I get 0 current. And then when I apply I guess this would be the Lorentz force, but when I say there's no current, there would be no force. So the force here is just a big fat 0. So nothing really to calculate there. And then we can do C as it's leaving by kind of arguing that isn't leaving just like going in. And I would say yes, with the exception of we're losing flux instead of gaining flux. But in terms of magnitude, I'll start there, everything's going to be the same in C as it was in A. We're going to say something like this. Here's the EMF. And if I do the magnitude of the EMF, it's the number of turns. That hasn't changed. It's the derivative of the change in the flux. And this right here would be the B dA cosine of 0 degrees when it's leaving. In fact, if I drew a picture, it would be over here, halfway in and halfway out as it's kind of leaving now. And then the argument would go just like it was in A, that we would have this B that we would pull forward. We would have the derivative, and the area then would be the width, and then how much is still remaining. So maybe I'd call now this the X. You know, how much of it is still remaining would be how much flux there is. But that would be changing. That would be decreasing, but without calling it a negative, because again, I'm just doing the absolute value. This would be the N, the B, and then the W I'd pull out, and then I'd have the dx dt again. And so this EMF is exactly the EMF we got when we did, you know, A. So going in or going out, the magnitude is still the same. Kind of makes sense. The change in flux is increasing as you're going in. It's decreasing as you're going out, but it's the same rate. And so right now I'm just calculating a magnitude, a rate. So it doesn't surprise me then in part C, I'm going to get the same EMF, and I'm going to have the same resistance, which means I get the same current. And so all of that is to say for number C, when I go I equals to L cross B, I'm going to have this I, this L, this B, and also then sine of 90 degrees. Now, coming to the picture, though, this I, as we just said, would be the N, the B, the W, the V, all over R. The L is, of course, the length of it. And so now I'm talking about the length of number 4 here. This is the one that's actually then in the magnetic field. Whoops, I shouldn't put an arrowhead because I haven't really said which way the current's moving. And I think it's now going to go the opposite way. But it is this one here. So this length would be the W and then the B. And then my argument that there would be a current in this top piece, and I'd only have to worry about the part that's in the magnetic field, and likewise here. And again, without saying which direction it is, I'm going to say that the top one and the bottom one are equal in magnitude, opposite in direction. and they're going to cancel each other off, and there is no force in wire number 2 because it's outside of the magnetic field. So again, I'm just repeating everything I said for part A. I'm just now looking at wire number, what I called wire number 4 here. Now, I'll also say one more thing like I did last time. To get the total force, I'd have to multiply by n, because there really is n of these downward or upward. I haven't said which way the current's going yet, but that's the current in there. So you end up with the same thing. You have an n squared, you have a b squared, you have a w squared, you have a v, you have an r. So that's exactly, where did we do A on page 2, what we got before, or at least in magnitude. But again, it should be slowing it down. If it doesn't slow it down, I've got real major concerns about conservation of energy. And so my cheater's way of doing Lenz's law is to say, look, it's got to slow it down. I may not understand all the details of the flux, but it's still got to be in the negative I-hat direction. Because if it's not, then somehow this thing, as it exits, gains kinetic energy, and at the same time it's making current, so it's gaining kinetic energy and producing heat. Where in the world does that energy come from? And there is no answer to that, so it would be a violation of conservation of energy. And so I'm quite sure that, even though I haven't done it yet, that I'm going to get a negative I-hat for the direction. So it slows down as it is leaving. So it slowed down not only as it was entering, because like I said, it made electricity, which made heat. And the energy of heat came from the kinetic motion of this wire. Then it would go across at a constant speed, but as it's exiting, it would also slow down. So whether entering or exiting, it's got to be slowing down. I'm sure of it. But let's go through Lenz's law to prove it. And let's start with the direction of the current. So if I were to draw a couple of X's in here to represent the magnetic field, oops, wrong side. As this thing is leaving, there now would be fewer magnetic fields going in. So that tells me the current is set up either clockwise or counterclockwise in such a way to oppose the change. That's what technically Lenz's law is saying. It says that the induced current will be in such a way that it will oppose the change. I like to say then the secondary field will be in such a way to counterbalance the change. So in this case, the primary is changing by getting less and less going in. So that tells me the secondary will be set up so that it goes in. So I'm going to use right-hand rule number 2, and I'm going to point my thumb in. Okay? And that is then telling me that the current that's in the loop is set up so that the secondary field is going in to make up for the loss of the primary. And so the induced current opposes the change. So this is in a clockwise direction. So as I look at my fingers, this is a clockwise direction. And so I'm going to draw a little arrowhead for what I'll call the top wire from left to right, and then top to bottom for wire number 2, and then right to left for wire number 3, and then bottom to top for wire number 4. So as I kind of speculated, the current is in the opposite direction compared to when it was going in. So it was going in, it was going counterclockwise. Now coming out, it's in a clockwise direction. And as we already argued, there'd be no force from wire 2. Even though there's a current, it's not in the magnetic field. And the force from 1 and 3, we might as well label on here, but they're equal and opposite. And so you can kind of see from right-hand rule number 1, the L cross B. If I look at wire number 1, I'd put my fingers in the direction of the current closed towards the magnetic field, which is down, and my thumb is pointing up. And so the magnetic force on wire number 1 is up. And I'm pretty sure then wire number 3 is going to be down. Let's see. There's the current going this way. Good. And I'll close my fingers down towards the magnetic field. And my thumb then points down. Oh, and so, as I thought, 1 and 3 are equal and opposite. So they cancel off. It's the big one here is number 4. And so number 4, the current is going up. And so if I do this cross product here, put my fingers up and move my fingers down towards the field, and my thumb is pointing then to the left or the negative direction, slowing it down. And yep, sure enough, same thing. So yes, it should have the same force and actually the same direction. It's you know, to the left here, to the negative direction. All right, so good fun stuff. I'll say it again. Here's the new thing. That's hard enough in itself, but fortunately there's not too much. It's just Faraday's law and Lenz's law. But you got to put that together with Ohm's law and the Lorentz force. And of course, that means you have the 2 right-hand rules going on, one getting the direction of the current and the other one doing this cross product. And so all of those can add up to a pretty complex problem when we have to put all of our past stuff that we learned together. And not to scare anyone, but you know, that's going to be really the rest of the semester. We're going to have both electric fields and magnetic fields going on here. And so and then sometimes 2 electric fields and sometimes 2 magnetic fields. And so the difficulties of keeping them track can get a bit complicated. All right. Hope that helps somebody.